Welcome to this next video in the playlist on topology. In this video what we're going to do is introduce the concept of a topological manifold. Okay, so in previous videos then in this playlist we've looked at the definition of a topological space, and I hope we're now familiar with the concept of a topological space. Now the concept of a topological space is very, very general. Okay, it's very, very broad, and there are an absolutely huge number of topological spaces, and a lot of them are absolutely useless, okay, as far as anyone has explored so far, so no one has got uses for them yet. Okay, indeed, mathematicians have failed so far to completely categorize topological spaces because there are so many of them. Okay, so i.e. there is no complete categorization of topological spaces where we have got every single topological space that exists categorized into a certain category. Okay, however, what we're going to look at in this video, topological manifolds, this is just a category of topological spaces. It's a bunch of very, very special topological spaces that have very nice properties that mean that these topological spaces warrant study and are actually useful. Okay, so that's what topological manifolds are going to be. They're just going to be topological spaces that obey an additional requirement. Okay, so an additional property they're going to have to obey in order to be a topological manifold. Okay, so let's try and understand then, let's try and motivate what this additional property is actually going to be. Okay, so far in this playlist on topology, we have seen a whole bunch of very special topological spaces. Okay, and those special topological spaces are the Rn topological spaces with the standard topology on. Okay, so the set is Rn, which means the real numbers Cartesian producted with the real numbers Cartesian producted with the real numbers n times overall. So that set of n tuples of real numbers along with the standard topology defined on it. And we know that the reason that these topological spaces are considered important, why they're called standard topologies, okay, the reason they're considered important is that the R1 with the standard topology is believed to mirror the structure of the one-dimensional continuum. R2 with the standard topology on it is believed to mirror the structure of the two-dimensional plane. Indeed, we could use the word, we believe they are homeomorphic to the two-dimensional plane. Okay, R3 we believe is homeomorphic to the three-dimensional continuum. So that's the reason that these Rn's with the standard topologies on them are considered special. Okay, now, what I want to do then is just do a little bit of a recap on this. Okay, so just, we're going to take one of these, we'll take R2 with the standard topology on it, and we'll remind ourselves of how we believe this mirrors the structure of the two-dimensional plane, and we'll have a look once again at the informal intuition as to what the topological structure of the two-dimensional plane actually is. Okay, because understanding, having a good intuition for these is going to be absolutely crucial to understanding what a topological manifold is. It's all about these. Okay, it's all about trying to extend these and build other topological spaces that are somehow related to these. Okay, so R2 then, so R2 with the standard topology on it. So this is a very abstract structure. Okay, we've created a set of symbols, all pairs of real numbers, and we've defined this very abstract structure on it, the standard topology, which remember is just a set of subsets of this. Okay, but what informally and intuitively is this actually trying to capture? Well, we believe that this is homeomorphic to the two-dimensional plane. So let's draw a picture here. Okay, so here is my picture of the two-dimensional plane, and we know that what we can do is we can associate the symbols here with points on the two-dimensional plane, and you could do this arbitrarily, but the way that is most usual is to do it in the Cartesian way, so form a nice grid here, and then let the two real numbers represent the coordinates on that grid. And then we believe that this standard topology is capturing the topological structure of the two-dimensional plane. Now, what is informally and intuitively the topological structure of the two-dimensional plane? Well, this is all about how the points on the two-dimensional plane are connected to each other. Okay, and of course the two-dimensional plane does have that sort of a notion. Okay, it's not just a set of points with no notion of which ones are connected to each other. There is a notion of how these are connected to each other. Obviously, when you look at the picture, okay, if there was no notion of how they were connected to each other, we wouldn't draw a picture like this. It wouldn't be right to draw a picture like this. Okay. Instead, imagine, I don't know, grains of sugar or grains of sand. Those you can imagine are the points of the plane. That is what it would mean for them to have no notion of which ones are connected to each other. Okay, so this does have a notion of which ones are connected to each other, but let's try and understand why it's necessary to employ such an abstract structure, this set of subsets of this set, to understand this notion of how points are connected to each other. And the reason for that is actually it's very difficult to capture symbolically how the points of this two-dimensional plane are connected to each other. And the reason is, if we take a point here, little p, okay, which points are next to that point P in this two-dimensional plane? Which points should I actually draw lines between this point P and those points? Which points are next to it? Okay, well, that has no answer, and the reason it has no answer is that you can zoom in and in and in and in and in forever, and you can always find points that are closer and closer and closer. At least we believe that that is the case. Of course, it might be the case in the future that we understand that that isn't the way reality works, that eventually there is some granular level to the universe. But we believe that you can zoom in and in and in forever. Okay, so it's very difficult to answer the question of which point should this point P be connected to. The informal intuition is that it's the points that are infinitesimally close to it. Okay, so the informal intuition is that you should somehow zoom in and in and in further than you could ever go. So zoom in forever and then go some more. Okay, and then the idea is that if you could zoom in to that infinitesimal level, you would see something that looks like this. Okay, a very nice lattice grid like so. So here, let's say that is our point P, so I think I'll just colour my point P in here. Okay, so here's my point P now, and this is the infinitesimal picture, which of course doesn't really exist, but we can intuitively understand it this way. Okay, and here, these points here are the points that are infinitesimally close to this point, and look, I've now drawn nice little connections between them, and these are the points that are next to this one. Okay, so that is the informal intuition for the topological structure of R2, that really it's just this incredible, beautiful lattice like so of points being connected to their neighbours, then points that are next to each other, going on with this beautiful lattice forever and ever and ever and ever and ever and ever and ever. That's the informal intuition for the topological structure of the two-dimensional plane. Now, of course, that is informal because these points don't actually exist. Okay, so how do you rigorously capture that informal intuition? Well, some genius long ago found a way to rigorously capture that informal intuition, and it's through this structure which we call the topology, okay, which is this set of subsets of the set R2. Okay, and that does amazingly capture this informal intuition for the way that points are actually connected or close to each other. Okay, so that's a reminder of the informal intuition as to the topological structure of the two-dimensional plane. And of course there is analogous informal intuition for R1 and R3 and generalizable to R4 and R5 abstractly. Okay, so that's a reminder then of R2 and more generally Rn with the standard topology. Now let me try and explain where we're going with this definition of a topological manifold. Okay, so this is a whole bunch of beautiful topological spaces. However, there are loads of topological spaces that are actually very, very similar to these ones in structure. Okay, although they're not the same, they're not homeomorphic to it. And we would like to include these ones in this definition of topological manifold. Okay, so let me give you some more pictures of some topological spaces that I want to be included in this definition of a topological manifold. Okay, so one of them is going to be the surface of the two-dimensional surface of a sphere here. Okay, so again, a nice intuitive one that we can all visualize. Okay, so this, again, intuitively, it is a topological space. It's a set, okay, you can give all the points on this two-dimensional surface, you can give them symbols and put all of those symbols into a set, and there is a notion of which points are connected to other points, just like there is a notion here. Okay, so this is not the same as this one. They're not the same topological space. The plane is not the same as the sphere. They are not topologically homeomorphic. You cannot turn this one into this one by stretching. Remember from the video on topological homeomorphisms, we saw that intuitively two topological spaces are identical to one another as far as the topological structure is concerned. If you can stretch one, imagine it's made of elastic, and you can stretch it and turn it into the other. And the reason for that is that when you just stretch a piece of elastic, although you change the geometrical structure of it, you change the distances between points on that piece of elastic, you don't change which points are fundamentally connected to other points, so you don't change the topological structure. However, I cannot stretch this and turn it into this, not without sticking bits together, okay? So you're not allowed to stick bits together or cut bits up, so you cannot turn these two into one another by either sticking or cutting, depending on which direction you're going in. Okay, so these two are not topologically homeomorphic, they are different topological spaces. However, this one actually has a lot in common with this one, and let me explore this in a bit more detail. If we take a point on this one, so here is my point P, and let's imagine doing the same thing as I did over here, the informal intuition which I did over here. Let's zoom in and in and in and in and in to an infinitesimal scale. What would we imagine that we would see here? Well, I claim that the picture would look exactly like this, and I hope that's intuitive to you. That yes, if you were to zoom in, it would just be a nice little lattice like this with the point connected to its neighbours, okay? It would just be a nice lattice of squares like this, okay? So locally, this one looks very similar to this one. It's just globally, when you look at the entire thing, that you can see, oh, this one curves round in a way that this doesn't. Okay, so it's only globally that they're different. Okay, and that's really the gist of what we're going to do with a topological manifold. We're going to say that these are topological spaces that locally look like these RNs with the standard topologies on. Okay, and the job of this video is to make that rigorous, to make that precise. Now, just before we do make that precise, let me just give you another example for something that I would like to be a topological manifold. Okay, so the surface of a torus is something I'd also like to be a topological manifold. Okay, so remember the torus is the surface of an American donut here, like so. Okay, again, a topological space that is not the same as this one, and it's not the same as this one. I cannot turn this one into the plane or the sphere just by stretching it, imagining it's made of elastic and stretching it. I'd have to cut bits up and stick bits back together potentially. Okay, I'd have to break the topological structure. Okay, and that's not allowed. As soon as you do that, you're no longer doing a topological homeomorphism. Okay, so a different topological space, but again, if I take a point on here and look locally at the structure of this, zoom in and in and in and in, what would I see? The same picture as before, okay? The same picture as I saw originally for the two-dimensional plane, R2 with the standard topology on it. Okay, so again, this one locally looks like R2 with the standard topology on it, even though globally, obviously, it's not the same. Okay, so again, this is going to be included in our definition of a topological manifold. Okay, right. So now what we want to do then is try to make this more precise. Okay, and before we actually go full on with making it precise, and we will do that, let me just try to make a little bit more clear what I mean by these locally being the same as these. Okay, so if we were to look at an open set, for instance, on the sphere, so we'll work with this topological space, the surface of the sphere here. What does an open set on this topological space look like? So we've talked about the informal intuition for this topological space. Now let's talk about the rigorous account of this topological space. What does an open set actually look like on here? Well, an open set is going to look very similar to what an open set looks like in here. It's going to be one of these sets that doesn't contain its boundary. So if I draw an open set that actually contains this point P, it'll look something like this. So there'll be all the points inside of that dashed line there, but not the actual boundary, so not the dashed line itself. Okay, so these subsets that visualizably don't contain their actual boundary, those are going to be the open sets for my topological space here. Okay, now what I hope you can appreciate is that as a topological space, so this open set, so let's give this open set a name, let's call it U. Now this fundamentally is a subset of the sphere here, okay, and we know that we can turn a subset of a topological space into a topological space in its own right. Okay, so we've had a video on topological subspaces, and we know that any subset, so it doesn't need to necessarily be an open set, it can be any subset you like, but since we've got an open set here, we can use that one. Okay, so we can use this open set, and what we can do is restrict the topology on here. Okay, and I'll call the topology just tau, and we'll restrict that down to the subset, which basically means take all of the open sets that were originally in the topology, intersect them with this subset, and stick those into the topology for this subset now, and that will be called the subset topology. So you can create the restricted version of the topology from the larger topological space for this subset and turn it into a topological space in its own right. So any subset does have a very natural topological structure in its own right. Now, that open set as a topological space in its own right is, I claim, topologically homeomorphic to an open set from R2. Okay, so if I have an open set from R2 over here, which I'll colour in red, so again, an open set from R2 will also look like this familiar visualizable picture of a set with no boundary. Okay, so it doesn't contain its own boundary. Okay, and again, this will be a topological space in its own right, because I can just, again, restrict the topological structure from the entire plane down to this. Okay, so I claim that this subset here will be topologically homeomorphic to a subset from R2 with its restricted topology on. Okay, and I hope that's intuitively obvious that if I do stretch this out, that I can turn it into a subset over here. Okay, right. Open sets in here, this is a nice open set in here, and I can turn that into an open set over here. Okay, they're topologically homeomorphic to open sets over here. Okay, now what I can do is I can completely cover this entire topological space with open sets that are topologically homeomorphic to open sets over here. Okay, so let me show this. So imagine dividing up, and they don't have to have empty intersections, so I'm just making lots of these open sets like so. Okay, and I'll colour these in a moment. Okay, so let's try and colour a few of these in. So here's one in turquoise, here's an open set. Okay, here is another open set in purple, and as I say, they don't have to have non-empty intersection. Okay, so the idea here is that I can get loads of open sets here from my topological space, this arbitrary topological space over here, and I can turn them into topological spaces in their own right, so I can restrict the topological structure of the entire topological space down to those open sets, and these subspaces, these topological subspaces of the larger topological space, they are all topologically homeomorphic to open sets in R2. Okay, so what is the intuition here? What do I mean by this? I mean that I can build this entire topological space out of this patchwork quilt of subspaces that are all topologically homeomorphic to open sets in R2. And that is going to be what we're going to make precise to form the definition of a topological manifold. A topological manifold, in this case of dimension 2, is going to be a patchwork quilt, basically, of subspaces which are topologically homeomorphic to open sets in R2. More generally, a n-dimensional topological manifold is going to be a patchwork quilt of subspaces that are homeomorphic to open sets in Rn, with the standard topology on it. Okay, so we'll have a break there, and in the next video what we'll do is make this precise.